Hey, today we're going to learn about the first derivative test, which is a technique for determining whether a critical point is a relative maximum, a relative minimum, or perhaps neither. And here's the careful statement of the first derivative test. Suppose you've found some critical point c of some continuous function f. Then if the derivative changes from positive to negative at c, that means that f has a local maximum at c. If the derivative changes from negative to positive at c, then f has a local minimum at c, and if the derivative doesn't change sign at all at c, then the function doesn't have any kind of extremum, any kind of local extremum at c. And here's the basic idea. Picture some function f, like this one that I've sketched in right here, and you do a little work and you find that its critical points are at these 2 points that I've labeled c1 and c2 here. Well, if you look at what happens at c1, well, to the left of c1, the function is increasing. And so by that third corollary to the mean value theorem, that means that the derivative is positive to the left of c1. To the right of c1, the function is decreasing. So by that same corollary, the derivative is negative to the right of c1. And so the derivative has changed from positive to negative at c1, and so there's a local maximum there. Similarly, at c2, to the left of it, the derivative is negative, the function is decreasing, and then the function is increasing, so the derivative is positive to the right of c2, and that tells us that there's a local minimum at c2. Let's do an example. We'll take the function f of x equals x to the fourth minus 8x squared plus 1, and we'll see if we can find all of the relative extrema. And the first step is to find the critical points. And to find the critical points, we take the derivative and we set it equal to 0 and we solve. You do that algebra and you get that there are critical points at x equals 0, x equals 2, and x equals negative 2. And now we need to know what happens to the left and right of each of those critical points. So we make ourselves a little chart. And the chart is of x values and values of the derivative, and we certainly want to include the critical points in the chart, and we know the values of the derivative at the critical points. The values are the derivative is 0 at the critical points, that's why they're critical points. And now I need to pick points to the left and right of each critical point. Let's start with a point to the left of negative 2. And suppose, for example, that I pick negative 5 as my x value to the left of negative 2. I'm interested in the derivative at negative 5, but in particular, I'm interested in whether the derivative is positive or negative at negative 5. And the key here is that the derivative itself is a continuous function. And so if the derivative is, say, positive at negative 5, then it can't possibly be negative at some other point to the left of negative 2, because if it was positive at one point to the left of negative 2 and negative at some other point to the left of negative 2, it would have to be 0 somewhere in between those points by the intermediate value theorem. And it's not. We've already found all the places where the derivative is 0. It's only at these three values, negative 2, 0, and 2. Which is to say, if I determine whether the derivative is positive or negative at negative 5, that determines if it's positive or negative for all the values to the left of negative 2. And one way, and perhaps the most straightforward way to do this, is to just take negative 5 and plug it into our expression for the derivative. The derivative is 4x cubed minus 16x, and you get that it's negative 520, or a negative number, and that's all we needed to know. It's negative at negative 5. But that's a lot of work, and in particular, that's a lot of arithmetic. And the arithmetic is only going to get harder as the functions get more complicated. And so it would be better if we had a simpler way to compute this. And luckily, we do. In order to find the critical points, we had to factor the derivative. And so the derivative, it's true that the derivative is 4x cubed minus 16x, but the derivative is also 4x times x minus 2 times x plus 2. And so we can use that expression for the derivative and see what happens to each of those factors at x equals negative 5. Well, 4 times negative 5 is a negative number. And negative 5 minus 2 is a negative number. and negative 5 plus 2 is a negative number. And when you multiply three negative numbers together, you get a negative number. And that's all we needed to know, is that the derivative at negative 5 is negative. Okay, let's pick some value between negative 2 and 0. Negative 1 seems like a reasonable choice. And we can compute f prime of negative 1 the same way. I don't need to know the exact value of f prime of negative 1. I just need to know whether it's positive or negative. Well, 4 times negative 1 is negative, and negative 1 minus 2 is negative, and negative 1 plus 2 is positive. And a negative times a positive is positive, and so we get that the derivative at negative 1 is positive. Similarly, I'll pick a value between 0 and 2, let's say 1, and I'll pick a value to the right of 2. I could pick 3, but let's pick 500 just to show that it doesn't really matter. Computing the derivative at 1, when x equals 1, 4 times 1 is positive, 1 minus 2 is negative, and 1 plus 2 is positive, and a positive times a positive is negative, and so we get that the derivative at 1 is negative. And then computing the derivative at 500, we get, well, 4 times 500 is positive, 500 minus 2 is positive, and 500 plus 2 is positive, and a positive times a positive is positive. So the derivative at 500 and everywhere to the right of 2 is positive. And here's what this tells us. It tells us the function is decreasing to the left of negative 2, hits a critical point at negative 2, and is then increasing to the right of negative 2 and the left of 0, and then decreasing again to the right of 0 and the left of 2, and then increasing again to the right of 2. And what we've just done is use the first derivative test, and we can conclude that this function has relative minima at x equals negative 2 and x equals positive 2, and a relative maximum at x equals 0. And here's the function we've been talking about, f of x equals x to the fourth minus 8x squared plus 1, and you can see clearly the local minima at negative 2 and positive 2, and the local or relative maximum at x equals 0. Just one quick word of caution, this clever trick that we're using here, where we compute whether the derivative is positive or negative just by plugging in the value to the factors of the derivative, only works because they're factors of the derivative. They're multiplied by each other. In other words, a negative times a positive is always a negative. You can't think that you can do the same thing and look at just the derivative written out something like this and plug in some number and try to do something similar, because a negative plus a positive or a negative minus a positive might be negative or positive. You don't know. You have to look at the factored form of the derivative in order to do the cleverness with simplifying the arithmetic that we were just doing. You also have to be a little bit careful in that when you're solving for the critical points, we could easily have divided both sides by this 4 and gotten the same critical points. In this particular case, that wouldn't have changed our results. But if, for example, that had been a negative 4 and you divided both sides by negative 4, you'd get the same critical points. But when you went over here to try to compute whether the derivative is positive or negative, you'd get exactly the wrong answer every time. So in other words, what I'm saying is, don't factor out the constant just to find the critical points. Leave it in there so that you get an expression like we have right here that really does precisely describe the derivative, not the derivative but without some leading constant. That way you're sure to get the signs correct when you plug values in. Okay, you try this one. Take the function f of x equals x to the fourth plus 4x cubed and use the first derivative test to determine all the relative extrema of this function. So pause the video, do all the work, and when you're ready, start it back up again and we'll look at it together. You start by finding the critical points, so you take the derivative, set it equal to 0, and solve, and you find that we have critical points at x equals 0 and x equals -3. You also find along the way that the derivative is equal to 4x squared times x plus 3, and that will be useful information as we make our chart to try to determine whether these critical points are relative extrema. We start our chart by putting in the x values of the critical points. We know the derivative at those points are 0, and now we need points to the left and right of each of those critical points. And so I picked some, -5 to the left of -3, -1 between -3 and 0, and 2 to the right of 0. You certainly could have picked others. You'll get the same results. And if you evaluate the derivative at -5, you find that 4 times -5 squared is positive, and -5 plus 3 is negative, and a positive times a negative is negative. And so that's why I've put a negative sign under the -5. Similarly, the derivative at -1, 4 times -1 squared, also positive. In fact, that term is always going to be positive because it's got that x squared, so that's always going to be positive. And then -1 plus 3 is also positive, and a positive times a positive is positive. And so at -1, the derivative is positive. And by similar logic, the derivative at +2, also positive. And so we have that the function is decreasing to the left of -3, and then hits the critical point there, and then starts increasing, and then hits the critical point at 0, and then continues to increase. That's what this is telling us. And so by the first derivative test, this function has a relative minimum at x equals -3, and doesn't have any kind of relative extremum, neither a maximum nor a minimum at x equals 0. And here's the function. You can see the relative minimum at x equals -3, and you can see why there's a critical point at x equals 0. A tangent line at x equals 0 would be horizontal, so the derivative at x equals 0 is equal to 0. But the function is increasing to the left of 0 and increasing again to the right of 0, and so what's happening at 0 there is not a relative maximum and not a relative minimum. Okay, try one more and then we'll call it a day. See if you can find all of the relative extrema of this function, f of x equals x squared e to the 3x. So pause the video, take your time, work it out, and when you're ready, start it back up again. We need to start by finding the critical points. So to find the critical points, you take the derivative. You need the product rule to find the derivative, so you use that. And then you take that derivative and you set it equal to 0 and solve. And to do that, you have to factor the derivative. So you do that, and you get that the factors are x, e to the 3x, and 2 plus 3x. And when you're multiplying three things together and getting 0, one or the other of them must be 0. And so either x is 0, which gives you one critical point, or e to the 3x is 0, which never happens. E to the 3x is always positive. E to the x is always positive. And so there are no critical points that arise from that factor. And then the last factor, 2 plus 3x, gives us the critical point, x equals -2/3. And just to point out, the other bit of useful information that we've picked up here is that the derivative factors as x e to the 3x times the quantity 2 plus 3x. Okay, to apply the first derivative test, we need a table of x values and values of the derivative. We want our two critical points in this table, and we know that the derivative at the critical points is equal to 0. We then have to pick points to the left and right of these critical points. To the left of -2/3, I'll pick -1. Between -2/3 and 0, it's a little bit trickier, and you'd like to come up with a value that will make the arithmetic easier. There's plenty of different values to choose from, but if you look at the expression for the derivative, it looks like if we picked x equals -1/3, that might make the arithmetic just a little bit easier for us. And to the right of 0, I'll pick 1. Could have picked any number to the right of 0, but 1 will probably be easy to work with. We have our factored form of the derivative, And from that, it's easy to compute f prime of -1. When you plug -1 in for x, the x becomes negative because it's -1. E to the -3 is 1 over e cubed. That's a positive number. E to anything is always a positive number. And then 2 plus 3 times -1 is a negative number. So we get a negative times a positive times a negative, and that's a positive. And so the derivative is positive at x equals -1. Computing the derivative of -1/3, well, -1/3 is a negative number. That's the first factor. And then there's e to the 3 times -1/3, or e to the -1. That's 1 over e, a positive number. And then 2 plus 3 times -1/3 is 2 minus 1, which is a positive number. And so we have a negative times a positive times a positive, and that's negative. And so we have the derivative at -1/3 is negative. And similarly, if you compute the derivative at 1, you get a positive number for each of the factors, and so the derivative at 1 is positive. And this tells us that the function is increasing to the left of the critical point at -2/3, and then decreasing between the critical points at -2/3 and 0, and then increasing again once we move to the right of the critical point at 0. And so we can conclude that this function f has a relative maximum at x equals -2/3 and a relative minimum at x equals 0. And if we wanted to know the x and y coordinates of these points, like to plot them on a graph, for example, here we've just found the x values. To find the y values, we'd plug them into the original function f of x equals x squared e to the 3x. That would tell us the y values, and we could plot these extrema on a graph. And that's what we are heading towards, taking all the information that we've learned about functions and trying to figure out how to sketch graphs of them. We will hold off on looking at a graph of this function until we're ready to sketch one ourselves. Okay, that was the first derivative test. Once again, it's a technique for determining whether a critical point is a relative maximum or relative minimum or neither. There's a homework on it. Have some fun with it. Look forward to seeing you in class. Bye.